chapter 11 just to kind of keep on pace. And then obviously we'll stop, and then it is exam day today, right? So um, we'll take it at the start of lab like we normally do. And then that will be it, I think, for today. We're in our final 2 weeks, I think. So this week and then next week and all that good stuff. Hopefully you had a good break. Okay, so this is chapter 11, which is kinetics, and it is the final chapter of the season here. And again, the notes should be up there. So, in this chapter, we're going to talk about chemical kinetics. And so, kinetics really does deal with sort of how fast the reaction takes place. So, there's two sort of things that we kind of talk about in chemistry, not so much in this class anymore. The first one, but the first one is thermodynamics. So we talked a little bit about some thermodynamics, which is energy, a lot of it. When you take 200B, we'll talk about things like entropy, which is sort of the disorder. I'll talk about things like Gibbs free energy, which is energy available to do some type of work. And a lot of times when you deal with thermodynamics, as you'll see in 200B, you're oftentimes asking questions like, really, does this reaction take place? Is this reaction spontaneous? And when we talk about a reaction sort of being spontaneous, sometimes people misunderstand, sort of what that means. Sometimes we associate a reaction being spontaneous as a reaction that happens like super fast. And that's really not what it means. When you find out that a reaction is spontaneous, it means that essentially under those conditions that you're talking about, you would expect that reaction to actually take place. Again, it could take place really fast, it could take place really slow, but under those set of conditions, you would, expect it to actually occur. There's a lot of reactions that are spontaneous, but, takes forever for it to actually sort of take place and occur. So, for example, ammonia, the production of ammonia is actually a really slow reaction unless you add something like a catalyst to speed it up, but it will sort of happen. So the area that we're going to talk about sort of in this chapter, and that really does deal with sort of how fast a reaction occurs, is what's known as kinetics. So in kinetics, we kind of look at, how fast, or I guess how slow, a particular reaction may occur. And when we talk about reactions occurring fast or slow, a lot of times what we talk about is what is referred to as the reaction rate. And the reaction rate is basically most of the time the change in the concentration of a reactant or product over a period of time. So a lot of times what we end up with are the units that we see here, which are molarity, which is obviously a unit of concentration, over seconds, which is obviously a unit of time. So molarity over seconds, and sort of the change in molarity over seconds, again, giving us our concentration over time sort of relationship and how it's changing. So if we look at a particular reaction of A going to B, A being our reactants, obviously B being our products, we could assume that this reaction is heading, towards the product side in this particular case. And what we would expect to sort of happen in this case is we would expect that the amount of A should start to decrease with time. Again, we need to basically use our reactants to actually start producing some of our products. So we would expect the amount of B to actually increase with time. And we can basically write a relationship that basically describes that. And that's what's sometimes referred to as a rate expression. And this is sort of part of a rate expression that we see here on the left. We could say that the rate of this reaction is equal to minus the change in the concentration of A over the change in time. So when you see, again, these sort of brackets, that means concentration. And basically, in most cases, we're talking about molarity, which is our moles per liter. So it's the change in the concentration of A over the change in time. That's what the delta is. And we do have a negative here because it is a reactant, which means as this reaction proceeds, we would expect that it should start to actually decrease with time. We could also write it for our products, basically sort of the same condition here. The rate is equal to the change in the concentration of B over the change in time. The difference is here we do not have a negative, and that's because we should expect the amount of B to be increasing with time. So if we just kind of look at this reaction, for example, of A going to B, let's just say we started with 4 molar of A and 0 of B. And as this reaction ends, we end up with 2 molar of A, and we'll go with 3 molar of B. So if we were to calculate something like change in the concentration of A, we would do our final minus our initial. So this would be 2 minus 4 molar, which gives us negative 2 molar. It basically went down by 2. And that difference where you get a negative here is really why we have a negative here. That is because when you calculate the actual rate for a reaction, it should usually be a positive number. So that negative is there basically to turn it into a positive number. And we don't really need that here with our product because, again, if we did the same calculation for B, we took our final concentration versus our initial concentration. Our final concentration in this case would be 3 molar minus 0 molar, gives us a positive 3 molar. And obviously that gives us a positive rate. So whenever you sort of calculate the actual rate for a reaction, it should really be a positive number. And again, that's why we have the negative here when we write the rate expression for our reactants, because it is decreasing with time, which means when you do the change in the concentration, you should end up with a negative number. Those two negative values will basically turn it into a positive rate, which is essentially what you should expect to see. Any questions on that there? So when we talk about sort of kinetics, there's lots of graphs and stuff that we typically see, but we could kind of just see visually here. We started out at time 0, which is A, molecule A here, represented by the black circles here. Our product, which is B, is the red, which is represented by some red circles starting to appear. And what we see is as this reaction proceeds from reactants to product, when we start, we pretty much have all reactants here, as we can see in this graph. As this reaction starts to happen, we're going to decrease the amount of reactants, and we do see an increase here, obviously, in the amount of products that are being made. And you can see that as we start getting some red circles in here, our black circles, which are our reactants, getting smaller, till we have mostly products happening here when this reaction is over. And that's sort of what we would expect to see. Again, a decrease in the amount of reactants. We should expect to see an increase in the amount of our products that are going to happen. So one very common way that we can sort of follow the change in concentration versus time, it occurs especially when we have some type of reaction that involves some type of solution that has a color to it. And when we have a solution that has some type of color to it, and maybe it goes from a solution that's reddish, like in this color, or oranges, to a sort of colorless solution at the end, we could actually follow the change in the absorbance value to see what's happening with our concentration. So in this particular sort of experiment here, the BR2 is this orangey reddish type color. And as this reaction proceeds to our product side in this direction, what we end up with on our product side is pretty much stuff that has no color. So this colorless over here, as we can see in this sort of last beaker. And we got various shades of sort of the color going away as this reaction is proceeding. And we could use absorbance like a spec 20, like we saw in that one experiment when we did the Kool-Aid experiment. We could use something like Beer's law, which is A is equal to B times C. A is absorbance. B is what is sometimes referred to as Beer's constant. And C is concentration. And if you remember, basically in that sort of experiment, as we talked about, basically all this sort of spectrophotometry works the same way. You have a light source that basically shines a light at a specific wavelength through a sample. It goes through the detector, and we can measure two things. We either measure absorbance, which is basically how much light gets absorbed by the solution, or you can measure percent transmittance, which is basically the ratio of light that went in to the ratio of light that reached the detector. And what we know is sort of the darker color of the solution, the more light's going to be basically absorbed by the solution. So if we were looking at sort of our samples here, this guy over here would have probably the highest absorbance. And obviously this guy at this end would definitely have the lowest absorbance. And we could use sort of the advantage of this solution that has this color change to really follow what's happening with concentration. So for example, if we want to know sort of what's happening with Br2, since it's responsible for this reddish orange color, we know that as the absorbance values start to drop, we should have less and less Br2 there, which would imply that we're making more of our products, and this reaction is basically going to the end. Over here, something we also saw, I think, in that experiment, when we do set our spectrophotometer, we always want to set it to the maximum absorbance. So that is the wavelength that would be somewhere in this area here. Again, when we do that, that allows all of our samples really to be on scale and not sort of go off of scale. Again, if we set the wavelength down here, there would be a lot of samples that would absorb outside of the range of our guy. Lastly, as well, we also talked about the idea of, I think, complementary colors. So remember that the color of the solution that we see is complementary to the light that's being absorbed. So in this particular case, kind of orangey red, we wouldn't set the wavelength to the red or orange part of the visible part of the spectrum. We would set it to its complementary color in that sort of color wheel spectrum of it. But what we could do is use something like Beer's law, and we could really follow the change in absorbance values over a period of time. So every so many seconds, for example, you could take an absorbance reading, and you could have basically how the concentration is changing in the solution by following the change in absorbance values. Because again, the absorbance values is proportional. So that's what the little symbol there is for, proportional to the change in the concentration of Br2. So again, the higher the absorbance value, you should have a lot of Br2. The lower the absorbance value over time as it starts dropping, we should expect less Br2 to be there. And obviously, we should expect more products to be made in that particular case. Any questions on that? This is also why, as well, obviously, you could not use something like a spec 20 to do this type of experiment if your solutions were colorless, because you would get no absorbance values or anything like that in that particular case. So if we sort of graph what's going on in this particular example here, we can see that we have two types of rates. We have sort of an average rate, and we have sort of an instantaneous rate that's happening. You can figure out sort of those instantaneous rates by taking the slope of the tangent of that line there. That seems very mathematical, but we do have sort of two different types of rates that are happening. So it's kind of like when you drive, for example, if you drive somewhere and, the speed limit, say 65 miles per hour, perhaps there's points along that trip that you're not doing 65 miles per hour, maybe you're doing 70, 75, 80, hopefully not 90 or 100 or anything like that. And hopefully, if you are doing the really fast driving, there's nobody behind you to give you a ticket right at that particular point in time. But if you average it out over sort of the entire trip, perhaps you did drive about 65 miles per hour. But again, there could take sort of a window of time in that trip where you are obviously traveling maybe a little faster, maybe a little bit slower. And that would be sort of an instantaneous rate, which is a rate over a specific sort of instance in time. The average rate, again, is usually sort of calculated over the entire sort of experiment, if you will. And we do, like, for example, the change in the concentration of Br2 over time. So final minus initial. And again, since this is a reactant, that's why we have the negative, because again, this should give us a negative. And as I mentioned earlier, you should always end up with a positive number here for your average rate. Now, when we look at this reaction here, we do see a couple of things that's very important in terms of sort of kinetics. The first thing is we do see a relationship that is sort of constant, and we do see one that's really not constant. We do see that sort of the initial rates here they do sort of vary all the way across here, depending on sort of what period of time you're looking at. So that's sort of what we were just talking about. If you pick just sort of a window of time, there's a lot of variation in terms of how fast it may be going at that point. But there is a relationship where we do get sort of a constant sort of rate of time, and that is what is known as K, and that is the little k here, and I'll write it really little to emphasize it. This is what is known as the rate constant, and that's what we use here in kinetics, and it should not be confused with, as you would take 200B, I'll write it giant, it's not usually this giant, big K. Big K is the equilibrium constant, which is definitely something different. So that is 200B material here. So there really actually is a difference in terms of K. So lowercase k is what we're talking about in this chapter, deals with the rate constant, sort of describes how fast or slow a reaction is sort of taking place. We could write what is sometimes referred to as like a rate law here, and that is the rate is equal to the rate constant, in this particular case, times the concentration of Br2. And you can see in this particular reaction here, we do end up obviously with a relatively constant number for that, hence why it is called the rate constant. And it is specific for that reaction at that specific temperature. You will get basically a constant value when you do solve for the rate constant. We also see here that this rate constant has units of 1/seconds, and that also will give you some information in kinetics, as we'll talk about later in this chapter as well. If you get a rate constant that has units of reciprocal seconds, 1/seconds, 1 over some type of unit of time, that usually implies that this reaction is what is referred to as a first order reaction. And we'll talk about sort of what that means a little bit later on in this chapter as well. So the value of K is important. It kind of, again, like I said, gives you an idea as to sort of what is going on in terms of the rate of the reaction. But also very important in this chapter is the units that you see associated with those rate constants. It gives you a hint as to sort of what type of reaction you're dealing with. And that's really important later on as well, because there's specific sort of equations that you have to use depending on whether it's sort of first order, second order, or zero order reaction. As I mentioned earlier, not all reactions do, for example, produce a solution that has color, or starts with a solution that has color and ends with no color. So in cases where you might not have a solution or be able to sort of follow the change in color, there are other ways that you could sort of follow the rate of a reaction. So this is an example of a reaction where we're actually producing a gas. So in this case, well, hydrogen peroxide going through a decomposition reaction, going to produce some oxygen gas in here. We have it set up here so they could actually follow the pressure change that's happening in this particular case. So we could actually use the ideal gas law and sort of rearrange it like we've done before. So if you remember, if we rearrange this for N divided by V, which equals P over RT, N is moles and V is liters. So again, here we could use the ideal gas law, and we could really follow the change in pressure here and figure out how the concentration of that gas is basically changing. R is a constant. The temperature of this reaction would probably be done at sort of a constant temperature. So this allows us a very sort of convenient way to follow the rate of this reaction by actually following the change in pressure over time. And we could relate it basically to how the concentration of O2 is changing, as O2 is the only gas that's here. So obviously the only way that we would get pressure is to produce some O2 gas. So we know that we're definitely producing this over time, and we could look at the change in pressure over the change in time. Again, these two guys would be constants in this case. And we could really relate it back to really how molarity over seconds, for example, how the concentration of O2 is changing over time. In this particular case, we would expect it to be increasing with time. It is a product, so we would be expecting the pressure to start to increase, thus indicating that we are producing oxygen gas in this reaction. So this is another way that you could kind of follow a rate of a reaction. Again, in a case where we might not have a way to use spectrophotometry and absorbance to do that, we could actually do it through this type of method. Any questions on that? Okay, so We also want to take into account when we look at reactions, our favorite thing, which is stoichiometry. So even with sort of rates and reaction rates and how a reaction takes place, how fast or slow, we do have to take into account basically the stoichiometry that's involved. And in this particular case here, in this example here, we have 2A going to B. Our mole to mole relationship is for every 2 moles of A, we get 1 mole of B. So we do have to take that into account. And also when we write what is referred to as the rate expression here, and we would write something like the rate is equal to minus 1 over 2, the change in the concentration of A over the change in time. A couple of things here, minus because A is a reactant. So again, as we talked about before, should be decreasing with time. This 1 is 1 over the coefficient. So we take 1 over the coefficient, which is the 2 here. And what that does is it actually takes care of all of the mole to mole relationship, the stoichiometry, all sort of bundled together in sort of one calculation. The change in concentration A over change in T. For B, which is our product, we could do the same thing. Again, no negative here because it's a product. So it should be increasing with time. We actually have no 1 over anything because the coefficient here is 1. That gives us 1 over 1, which is obviously 1. So that's why there's nothing here for the coefficient because it is 1, the change in concentration of A over change in time. We could basically do that for a generic equation here. And what that allows us to do is basically take the rate is equal minus 1 over A for our reactant. Change in A over time equals minus 1 over B, also a reactant. So we have our negatives here. And then also our products where we don't have the negatives here. But what this allows you to do is basically you could relate how everybody in a reaction is changing using what we see here, which is sometimes referred to as a rate expression. So a rate expression is a way that we can basically relate everybody in a chemical reaction, how they are changing over. And really, we could do this by only knowing one piece of information. So if we know the rate, we pretty much could figure out everybody else here. Or if we know any one of those guys on the right, because we could set them all equal to each other, we definitely can figure out how everybody else is changing with time. So it's a very convenient way to figure out how everybody's changing in a reaction. Again, by just really knowing how one thing is changing, you could do that. You can use these coefficients, again, 1 over the coefficient. That takes care of the stoichiometry part. You can actually do the stoichiometry part kind of separate, um, but it's sometimes better to kind of do it together here. And again, a reminder, when you calculate the rate of a reaction or the average rate of a reaction, should be a positive number is what you should end up with here. Our reactants can be negative numbers, should be negative numbers, and our products should be positive numbers as to how they are changing. So if we wanted to write the rate expression for this particular reaction, we could say that the rate is equal to minus the change in the concentration of CH4 over the change in time, minus, because this is a reactant, is technically 1 over 1 here. So that's why I don't have anything happening there. That would also be equal to minus, again, because O2 is a reactant, 1 over 2, which is our coefficient here. Again, that takes care of the mole to mole relationship, the change in the concentration of O2 over the change in time. We could also set that equal to our products, which would be a change in the concentration of CO2 over the change in time. Again, positive because this is a product. Coefficient is 1, which is why we don't have any 1 over anything. It's basically 1 over 1. And for our last guy, we do 1 over 2, change in the concentration of H2O over the change in time. So again, if we just knew one piece of information, some numbers about somebody there, we definitely could do some calculations and figure out how things are changing over a period of time. Any questions on how to do that? We could set them all equal to each other. We could use them all sort of separately as well. You know, you could do the rate is equal to minus 1 over 2, the change in the concentration of O2 over the change in time. You know, you could do the rate is equal to a change in the concentration of CO2 over the change in time. And you could do it for the last guy as well. So you can set them all equal to each other. You could just pull out the sort of relationship that you want. this rate number that you get here, here, and here, they're all the same number. So once you calculate it once, you have it for everybody else sort of in there. So why don't we try one where we actually do have some numbers. So why don't you take a second here and see what you come up with. For this reaction, the concentration of I minus changes from 1 molar to 0.868 molar in the first 10 seconds. Calculate the average rate for the first 10 seconds and what is the change in the concentration of H plus over the change in time. So it's kind of weirdly worded there, but this is what we're looking for, a change in concentration of H plus over the change in time. So we have our I minus that's changing. So our initial I minus, which is 1 molar. Our final I minus is 0.868. We're going for basically 10 seconds. And we want to know how H plus is changing over time. So we want to start with what was given to us, which is I minus. So if we just kind of pull out that relationship that we could get from the equation, we could say that the rate is equal to minus 1 over 3, the change in the concentration of I minus over the change in time. We also have a relationship that H plus, which is what we're looking for, which is the rate is equal to minus 1 over 2 change in the concentration of H plus over the change in time. So we do have enough information to kind of put into here. So we'll do that first. So the rate is equal to minus 1 over 3. Here again, we want to do final minus initial. So our final is 0.868 minus 1 molar divided by basically 10 minus 0, if you will, seconds. Again, when we do that, that's going to get us, what we got, 0.868 minus 1. That's going to give us a negative number. We want to divide it by 3, divided by 10, going to get us positive 0.0044. Again, negative number here, negative here, going to give us a positive number for rate, which is what we want. So the rate here, or the average rate of this reaction, would be 0. How many zeros did I have there? 2, I think. Yep. 0.0044. The units are molarity on top, seconds on the bottom, molarity over seconds here. So that is the rate for this reaction. And why that's important is that is actually this number right here. So that is the rate for our other relationship. So it's the same reaction, has the same overall rate. So now that we have basically this number here, we can now solve for what we're looking for. So we know that 0.0044 molar seconds is equal to minus 1 over 2, the change in the concentration of H plus over the change in time. This is ultimately what we are trying to solve for. So what we want to do is basically multiply by 2, but not just multiply by 2. We also need to take the negative to the other side as well. So we want to multiply by negative 2. And that gets us a change in the concentration of H plus over the change in time will equal minus, because the negative should come over, 0.0088 molar seconds. So minus 0.0088 molar seconds. Any questions on that?
Yeah, I had a question.
Yeah.
My question was, why do we drop a negative? So we did the iodine
Mhm.
ion, and we did the negative because it's a reactant. But why did we drop it for the rate? Are you saying the rate's always positive?
The rate should always end up being a positive number. And the reason why the reactants have this negative here is because always when you take a reactant, because it's decreasing with time, its final concentration is always going to be less than its initial concentration, right? because it starts up here and the reaction starts decreasing with time, which means that its final part where it ends will always be a lower number than where it started, which means whenever you do this part of the calculation, you will also always hit a negative number. So that negative and negative will turn our rate into a positive number, which is always what you want for the average rate, is a positive number. And you don't have to worry about that on the product side, because on the product side, it's the opposite thing happening. Where it starts is actually lower than where it ends. So when it ends, it's always going to be a higher number than when it started. So when you do final minus initial, you'll get a positive number. So that positive and the positive without the negative there gets you obviously the positive rate. So that's really why the reactant side has this negative here, is to turn our rate, overall average rate for the reaction, to a positive number, which is what it should be. But what you do see here is we're talking specifically, though, about a reactant like we were actually solving for in this particular problem. It should be actually negative because that's a reactant. So the way that specific reactant, the H plus, is changing with time is decreasing with time, and that's what the negative would represent there on that particular one.
Got it. Thank you.
You're welcome. Other questions on that? So I would say a lot of times people screw up on the should I multiply or divide by the two, So, if you kind of set it up so you can see it, you should hopefully be able to sort of manipulate it. If you want to do sort of a regular stoichiometry part, you can too. You could just do like a mole to mole relationship up front between I minus and H2 and not do the 1 over. So that's an alternative way you could kind of solve these problems. Just kind of do the stoichiometry part first and then kind of incorporate the rate part at the end. And they both should really give you the same answer. Why don't we try one more here? If we have we have 2.4 times 10 to the 2 grams. So NOBR, molar mass, is 109.91 grams per mole. Decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes. Find the average rate of production of BR2 in molarity per second. So we're basically looking at we're basically looking for this guy here. All right, take a minute or two to see what you come up with or in the problem. So obviously we're doing something with NOBR. We're also looking for BR2. So from the equation, we can write a couple of rate expressions. The rate is equal to minus 1 over 2 for our coefficient here. The change in the concentration of NOBR over the change in time. For our BR2, it's actually just the rate is equal to the change in the concentration of BR2 over the change in time. Here again, the coefficient is 1, so we don't have to worry about any 1 over anything because it obviously ends up being 1 as well. So really we have information about NOBR, and remember that this is basically molarity over seconds. So we have grams given to us, we have milliliters given to us, so we can figure out molarity from that. So we do have basically 200 milliliters, which is the same as 0.2 liters. We do need to convert our grams into moles, so that is 2.4 times 10 to the 2 grams. NOBR, they were nice enough to give us the molar mass there, which looks like it is 109.91 grams per mole. That's going to give us, looks like 2.18 moles of NOBR. And if I divide that by my volume here, I will then get the molarity of it as it's decomposing. And that would be 0.2 liters. So if I do that, I end up with something like 10.92 molar. Any questions on that part of it there? So we also want time in seconds. So our time's in minutes. So we probably want to do a little conversion on that as well. So we have 5 minutes. What do they say? A minute is 60 seconds, I think, still. And that's going to be 300 seconds. So we now have all the parts we need to actually go into this guy. So the rate is equal to minus 1 over 2. This is actually the change in concentration, which is minus 10.92 molar over our time, which is 300 seconds. So why did I make it minus here? I made it minus because this is a reactant and it should be decreasing with time. So that's why we do need the negative there, just simply because if we don't have it, we obviously are going to get a negative rate, and we need a positive rate there. So it actually is negative because this is most likely found by taking final minus initial, and that should usually give us a negative number. So kind of important to insert the negative there because of that. Again, otherwise you will end up with a negative rate, which you don't want in that particular case. Any questions on that?
It wasn't there initially. We just put it there
We,
because of
we
the
just put it there because basically this is a decomposition. So we basically got, as you can see there, basically, um, this guy breaking apart into a couple of things. So this guy, whatever his concentration is, that's going to be negatively because it's going to be decreasing with time. And again, just a good way to remember is you do need to end up with a positive number here. So even if you forgot that and end up with a negative, just turn it into a positive and you'll be okay in that particular case. Other questions on that? So we do get a number, and that number is 0.0182 molar seconds. And that would be the average rate here for this reaction. But we're also interested in how the BR2 production is. So earlier we saw that the BR2 production is equal to basically the rate. So we saw that the relationship is the rate is equal to the change in the concentration of BR2 over the change in time, which means that is that number right there. And that means that is also how our product is changing over a period of time. It is changing by the same number here, basically. So it is increasing at a rate of 0.0182 molarity per second in this particular reaction. Any questions on that particular one? And again, it's basically all one-to-one relationship there. So, it ends up being the same number in this particular case. Question on rate expressions or anything like that? As I mentioned before, you again could have done more of a stoichiometry sort of move. You could have done the stoichiometry move at this point, just like a normal stoichiometry problem, and did the 2 moles of NOBr to the 1 mole of Br2, and that would get you the moles of Br2, and then divide it, and that would put you down into here at that point. So you could have went that way and did a more traditional sort of stoichiometry part, and then sort of insert the kinetics aspect of it at that point, and with the seconds and all that, and you could kind of go that way with it too. They both should give you kind of the same answer. Any questions on that? All right, well, I think that's a good place to stop for today. I'll give you a chance to stretch, maybe get something to eat before the exam. Couple of things we got left. We got 3 days left, right? 2 days in a final, so that's not too bad. So Thursday, obviously, we'll continue lecturing on this. Then we got next Tuesday, and then our final would be obviously 1 week from Thursday on everything, I guess. Yeah. Any questions on anything happening? Okay. So the exam is obviously like normal sort of rules, no notes, people, any of those type of things. Yes, none of that stuff should be out. Make sure you use proctorial. Again, yourself and your little work area would be good. You'll have the normal type of stuff. So you'll have a periodic table, some conversions. Again, there should be some PDF files of that in case you can't see it or something like that that you could open and use. And same sort of format. So multiple choice part, then obviously a part where you have to show the work on those problems that need work. And again, make sure that you do upload that work immediately afterwards, not hours later or anything like that. So I don't have to zero you out on those things. I think everything should be pretty self-explanatory. Again, if you do have questions, you could contact me, but I think it's probably pretty self-explanatory. Anything that you need in terms of constant stuff like that will be up there. I'll look. There should be something for the final. So if it's not open, I'll pop it up here in the next day or so, and I'll put it up there on Canvas where all of our other stuff is. Also, the homework thing is up there as well. So make sure you do upload the homework if you haven't done so already. And other than that, obviously we don't have lab today. So have a good rest of your evening. Good luck on your exam. And I'll see everybody on Thursday, I think. Yeah.